All right, hello everyone. I'm Kaushik,
And I'm Trevor.
and this is our BME 450 project. So, to kind of explain the background of our project a little bit, we have to talk about what is Alzheimer's disease. And it's a brain disorder that often causes different levels of memory loss and degrades other mental functions, such as thinking, learning, and organizing. And typical methods of diagnosing this disease include examinations, which can be both physical and mental. Another form is performing lab blood tests. And the last form listed here is imaging, which is kind of the focus of our project, which will focus on um, comparing different MRI images of Alzheimer's patients.
So for our data set, we found one on Kaggle. Uh, it has four different classes, mild demented, moderate demented, non-demented, and very mild demented, which were four categories to put those MRI images into based on what the actual patient was diagnosed with and their medical image. There were 6,400 images in total, with 5,121 in the train and 1,279 in the test.
And to get to the pre-processing of our data set a little bit, first we imported the necessary packages and libraries, pretty standard stuff. And one additional step that we had to do was mount our Google Drive into Colab, because Colab is the platform in which we developed our algorithm. The second thing we did was import the data from our specific Google Drive folders into with an image loader. And finally, we defined a data loader to increase the amount of control we have over the data that we use for our training and testing data. And finally, we defined a neural network, a loss function, and an optimizer. The neural network that we finalized in our current model consists of two convolution networks and three linear layers. We also implemented that cross entropy loss function, which we kind of kept constant throughout all iterations of our model. And finally, we added an optimizer, specifically the Atom optimizer, which is an iterative optimization algorithm used to minimize the loss function during the training of neural networks.
In our training, we ended up using 10 epochs. We started at 10, we kind of went to a lower number, and then with the larger data set, we ended up going back to 10. Uh, After each optimization step, we printed the training loss to see how it iterated through each loop. Then we also outputted the overall loss at each epoch through a plot, which went with the training loss. And we ended up using the entirety of the initial training data set to achieve our results. For the testing section, we ended up outputting 8 images along with their ground truth just as a baseline. And then we outputted our expected results that the algorithm predicted, and then with those four and so beyond, we ended up calculating the accuracy of each class prediction.
So here are the results that we had from our testing algorithm, or our training and our testing algorithms. So on the left here, you can see the results from the different epochs, and the key takeaway is that the loss is decreasing with each iteration of the epochs. And the plot on the right shows how is just a visual of that exact same data, where it shows how significantly the loss significantly decreases between the first two and three epochs, and then kind of levels out at almost a zero, actually at a zero loss. And the bottom right code output shows how our during testing, the accuracy of our various images resulted in 100% at test accuracy. And the class specific accuracy is typically there to help us gauge which classes are performing the best in terms of training, in terms of testing. But here, all of it is 100%, so it's a pretty solid result.
This is just showing what the testing part of the model gave us. These are 8 images along with their ground truth, as well as the first four and their predictions.
So to kind of talk about what we changed with our model from start to finish, our initial neural net consisted of 3 linear layers. And as I mentioned, our current model consists of 2 convolution neural networks plus the 3 linear layers. And the addition of the convolution networks definitely helped increase the efficiency of our model, especially since we had such a high training data size, and it definitely would have taken a couple days to run with just linear layers. And we also increased the training size. We initially trained the model with 50 and then proceeded on to 100, and then ultimately ended up using our entire data set, which was 5,121 images in training. And along with the increases in training size, we also saw a significant improvement in the decrease of loss. As with a smaller training size, we saw a pretty high loss, or not. We saw a loss that didn't decrease as fast as it did with our training of the 5,000 images. And the last problem we had was that the very mild and moderate classes consistently had a high accuracy, with the other 2 classes having significantly lower accuracy. And that issue was also able to be resolved by just increasing the training data that was used. And one additional thing that I wanted to mention was that we had a training and testing split of 80-20, and that was just kind of a pretty standard training test split that's used in machine learning models.
In the future, to further increase the accuracy, if at all, for the model, we could also increase the sample size of both those training and testing parts of the full sample. We could also increase the amount of epochs to have a greater confidence in that 100% accuracy. One thing that our code could be lacking was a resizing of those initial images, just because our initial Kaggle data set, we were able to constantly rely on the fact that they all had this same exact size. So we were able to just skip that step entirely. If we were to use images that came from other sources, we would need to really make sure that everything was the exact same size before we got any errors. Then we can also, in the end, try to analyze other layers of the MRI images. Here, we were pretty constant on what part of the brain was being scanned. So it could be pretty accurate at this layer, but if we moved up a few, like a few units or down a few units, we might run into some issues. So training at those different layers could prove beneficial. And thank you.